Hello, and welcome to the video accompaniment for Chapter 7, Section 2 of our text. In this one, we're talking about prime numbers. So after reading through this section, watching this video, and working through some problems, you should be able to write a positive integer as a product of primes, understand why there are an infinite number of primes, and be aware of several unsolved problems involving primes. Together with this, I've compiled a few Numberphile videos. If you've never heard of Numberphile, it's a series of videos on YouTube that covers various topics in math. And I found some really fun ones for a couple of the unsolved problems that we'll talk about in this video. So I'll remind you again when we get there, and you'll see that right next to these videos in Blackboard. All right, let's get started. So as we saw in the divisibility rules video, a lot of the things we're doing now are sort of a more formal, more refined version of things that maybe you learned way in the past. And so prime numbers are one of these ideas, right? At some point, you learned that you can factorize any number into a product of primes, but maybe you've forgotten exactly what that means, and maybe you've even forgotten what it means for a number to be prime. So definition of prime is an integer that's at least 2, whose only positive integer divisors are 1 and p. So 1 and itself. Those are the only two things that divide the number. For example, we'll look at some more examples, but for example, 7 is prime because the only divisors of 7 are 1 and 7. Those are the only things that divide 7. 2 is prime. It's the only even prime, and that's because the only things that divide 2 are 1 and itself. So there's lots of primes. In fact, there's an infinite number of primes. And then the following result tells us something about numbers which aren't prime. So the fundamental theorem of arithmetic is that every positive integer, at least 2, is either prime itself, or we can write it as a product of primes that may not be distinct. So any integer, any arbitrary integer, we can write as just some product of k primes for some k. And moreover, this factorization is unique, except for maybe the order in which we write the factors. So for any given integer n, there's only one way to write it as a product of primes. For example, we can take the integer 33,660. By the way, this example appears in the book without really much explanation. So let's see how we can write this as a product of primes. I remember I learned this early on, this sort of tree thing. It might have even been 5th grade, something like this, but it's fun to kind of look at these things again when we have knowledge of proofs and more understanding of logic. So just for example, how can we express this number as a product of primes? Well, one thing I can do is I can use my divisibility test from the last video and just test it for different primes. So for example, I might add up the digits. 6 plus 6 is 12, plus 3 is 15, plus 3 is 18. That means I know that 3 divides this thing. And in fact, once I know that 3 divides it, I can divide it by 3 and obtain the other factor along with 3. So in this case, I'd get 11,220. So it's 3 times that. And then 11,220, I can do some divisibility tests on that. See how to break that down further. 5, 6. Again, I add them up. I do a digit sum and get a multiple of 3. And so 11,220 is a multiple of 3. Let's see. 3 times something is 11,220. I'm actually going to get my calculator out. 11,220 divided by 3 is what? 3,740. So this one is now 3 times 3,740. And now I can break down 3,740. This time I do a digit sum and I don't get a multiple of 3. What about an alternating digit sum? So that would be 0 minus 4 plus 7. So that's positive 3 minus 3. Oh, I actually get, this should be divisible by 11. And so let me try and divide it by 11. Yep, it is. That 11 test works. I get 11 times 340. Now 340, I mean, I also could have started with the fact that it ended in 0, which is even, and so the number's even. So now I can apply that here. 340 is what? 2 times 170. 2, oops, I'm not drawing my other arrows. 2 times 170. 170 we can break down as well. Oh boy, I'm running out of room. 2 times what now? 85. And then 85, uh-oh, I ran out. I'm gonna finish it over here. Sorry about that. 85, I can pull a 3 out of that. And what do I get left? Oh, no, I can't pull a 3 out of 85. I can pull a 5 out of 85, I meant. So that's what, 17? And 17 itself is prime. And so 3,660 is 3 times 11 times 2 times 2 times 5 times 17. And so maybe I'll write that in descending order. This is can be written as 17 times 11 times 5 times 2 squared times 3 squared. So as a product of primes. And we can do this with any number we want. When they get really, really big, it of course becomes harder, and actually factoring large numbers into products of primes is a computationally difficult task. And a lot of cryptographic systems use this fact. We'll talk about cryptography later on in this chapter. So how do we know if a number is prime? How can we detect a prime? Well, sort of the main way to do this is through testing if anything divides it. And so that's what a composite number is. If we can find something that divides it that isn't 1 and it's not itself, then that number is called composite. And so that's the same thing as not being prime. Composite if it's not prime. And the theorem that goes along with this is that if we have a composite number, or we have a composite number if and only if there exists integers a and b, such that a times b equals n. So that's all that's really saying is we can find two factors between 1 and n such that their product is n. That's what it means to be composite. Right, all this is saying is, like, for example, 35 is composite because 35 is equal to 5 times 7. I can break it down. So a corollary to this that'll help us is that n is a composite number, then n has a prime factor such that p is less than or equal to the square root of the number. So that is, when we're testing for something to be prime, this is telling us what we should test. We need to test, so this is saying if it's a composite number, we should be able to find a prime number, p, such that p is less than or equal to the square root of n. So the only things we have to test for it to be a prime are just those primes up to square root of n. And we'll check all of those and see if those divide our number n. And if not, then it's prime. And if one does, then we found a factor. So let's take a look at this in action. All right, let's take a look at the integer 113, and we're going to show that this is in fact a prime number. So how do I prove an integer is prime? Well, I should test all the numbers, but that last corollary really just told us we just need to check primes up to the square root of 113. So the square root of 113 is 10.63 about. Square root of 113 is about 10.63. So test primes p with 2 less than or equal to p less than or equal to 10. Right, it needs to be less than or equal to 10.63, hence it's less than or equal to 10. And so if I just write out the primes between 2 and 10, I'll know exactly what to test. So primes between 2 and 10, so this is my list to test: 2, 3, 5, and 7. So really, those are the only guys we need to test in order to detect if this is prime. So if none of these divide it, then it's prime. And if one of them does, then it's composite. So let's test this. 113 is not divisible by 2 because its last digit is odd. So we can rule that one out. It's not divisible by 2. How about 3? Well, 3, I'll do a digit sum. 3 plus 1 is 4, plus 1 is 5, which is not divisible by 3. So 113 is not divisible by 3. 113 is not divisible by 5 because the last digit is not a 5 or a 0. So we can get rid of that. And is it divisible by 7? Well, here maybe we can just check. 7 times, let's think, 7 times 12. No, let's do 7 times 14. 7. Right, since we don't have a rule for 7, it's a little bit harder, but we can see that, oh, here we go. 7 times 16 is 112. And so there's no way 113 could be divisible by 7. So 7 also does not work. It's not divisible by 7. Hence, 113 is prime. That's what that last corollary is telling us. It's giving us a primality test. But what we need in order for that to work is a big list of primes up to the square root of it. So if my numbers are really, really, really big and I want to test it to be a prime, that's again going to be computationally difficult to kind of check every single one of these other primes and test if it's divisible by that. And so there are other primality tests. I'll talk about those in a few slides, or at least point you in the right direction to find those. So the natural question arises, how many primes are there? And maybe you already know the answer, and I've sort of said it in a previous slide, that there are infinitely many primes. So here's a theorem, right? This is a fact that we think we know. There are infinitely many primes. Well, how do we prove something like this? How do we prove that there are infinitely many primes? What's amazing is at this point in the class, we can actually do that. We can prove this result that maybe you've known for a very long time, but maybe you don't know why it's true. Guess what? We can finally prove it, which is super exciting. Let's do it. So why are there infinitely many primes? How can we prove it? Let's go by contradiction. So infinitely many primes, right, is the same, is the negation of finitely many primes, right? So let's go by contradiction. So assume to the contrary that there are finitely many primes. So if there are finitely many primes, then there must be some finite list of primes. So let P1, P2, let's say there's a total of, I don't know, how about K primes, be the list of primes. So right, this is just kind of seems silly, but this is how contradiction works, right? It's like, well, it's something that seems so obvious, and if you assume the opposite of it, you get a lot of leverage, right? So that must mean if there are finitely many primes, that must mean there's some finite list, and so we have this list of primes P1 through Pk, and every single prime appears on that list. So how can I get a contradiction here? Well, there ought to be much bigger numbers than any one of these primes, right? If there's only finitely many, there's infinitely many numbers out there. What about really, really big ones? They're all somehow products of these ones. And in fact, what I'll do is I'll take the product of all of these and add 1 to it. Let n be P1 times P2 times P3 up through Pk. So that product plus 1. I'll just add 1 to it and we'll see what happens. Well, so let's say something first about this. Clearly n is bigger than pi for each I. 1 less than or equal to I less than or equal to k. Right, it must be bigger than each one of the primes because it's bigger than the product of all of them plus 1. And so what that means is that, well, one of these primes must divide it. Right, it can't be prime itself because it's bigger than anything on this list. So it can't be prime, it must be composite. And since it's composite, we know this theorem that we must be able to find some prime factor of it. Hence, so one of these guys, one of these pj's must divide it. So I'll say hence p sub j divides n for some j. One of those primes has to divide it. Oops, oops, oops. J less than or equal to k. All right, so what does that mean? Well, that means we can write n equals p sub j times, what do we want to put here? How about r? P sub j times r for some r in the integers. Right, that's what it means for p sub j to divide n. And so I'm going to write that. So n as p sub j times r. So what we have now is p sub j times r is p1 times p2 times p3 up through pk plus 1. So right, if you missed that, I'm taking n here, which is equal to this. So I'm subbing this in for n over here and writing that equation again down here. And now what I'm going to do is I'm going to subtract this big product of primes over. So this will look like p sub j times r minus p sub 1 times p sub 2 up through, and I'm going to pick out p sub j because I know p sub j is still in this list. So I'm going to write p sub j minus 1 times p sub j times p sub j plus 1, right? And then I'll keep going, times multiplication there, times p sub k, the last one, and that's all equal to 1. So just subtracting that over. And what I can do is I can factor out a p sub j here. So this is p sub j times r minus p sub 1, p sub 2 up through p sub j minus 1 times p sub j plus 1 times up through p sub k, and that's equal to 1. All right, the contradiction, if you think about this, is pretty apparent right here. So what do I have? I have a positive number written as p sub j times this thing. So this thing is clearly an integer because each part is an integer and I'm just subtracting them. So this is some integer. And so what this is telling me is that p sub j divides 1. I'm going to write it over here, sorry. Hence, p sub j divides 1. But that's impossible. P sub j, we know, is greater than or equal to 2 because it's a prime. Right? Each number on this list should be greater than or equal to 2. But that doesn't make any sense. How could something greater than or equal to 2 divide 1? So this is a contradiction. We've reached something that's impossible. P sub j can't divide 1, and yet here it divides 1. And so therefore, we have to conclude that there are infinitely many primes. How cool is that? So, if you want to explain this to someone, really what's going on here is if there is in order to prove this, assume there's a finite number, take the product of all of them and add 1. And the claim is that number would have to be prime, which contradicts the fact that you had a full list of primes. That's the idea. So even though we know there's an infinite number of primes, it still leaves the question, what's the largest prime that people know about that we've been able to show as prime? The largest number we've been able to actually prove as prime. In fact, there's a whole community of people that look for these things. So as of, I was looking this up, as of January 2020, so pretty recently, the next largest prime has been found. The largest prime number known is 2 to the 82,589,933 minus 1. So it's a big power of 2 minus 1, and this has been proved to be prime. So written in base 10, just a little fact about this, it'll have almost 25 million digits in it. So it's a pretty big number. And it's an example of a Mersenne prime, or a Mersenne prime, which is a prime of the form 2 to the n minus 1 for some n. And really that n is a prime itself. So the discovery of this and the proof that it is prime came out of this project called GIMPS, which is the Great Internet Mersenne Prime Search. So it's this cool project where you can sort of donate your computer to this prime number search, and if your computer happens to find the next prime, if your computer is the one that does it, you get credit for that prime. And so you can contribute your own computer to this if you want. Maybe some of you like to build your own computers, or maybe you want to build a little like a Raspberry, use a Raspberry Pi or something. I don't know what you can do with this. So I do encourage you, if you're interested in this, to look it up and maybe contribute even if you want to. The other thing I'll say here is that these Mersenne primes are really, really interesting, as well as how do they know? How do we know? How did we test this thing to be prime? I'll tell you what, we did not check. I should say they did not check all of the prime numbers up to the square root of this number, because even the square root of this number is massive. There's no way they checked all the primes up to that. So there are there are more clever primality tests than just checking all the primes up to the square root of the number. And so what I have for you is a Numberphile video for that. So I do encourage you to check that out if you're at least a little bit curious about how we know that this thing is prime, how people did that, and how they're searching for other primes. And along the way, you'll learn a little bit about GIMPs, and maybe that'll encourage you to go and check out that project. There's another one called Prime Grid, I believe, which is also pretty interesting. So we've reached a really cool point in this class, and especially here talking about integers, where we can start to talk about problems that no one's been able to solve, unsolved problems in mathematics. And specifically, we're talking about primes here. There's just a slew of unsolved problems about prime numbers. Prime numbers, despite the 2,000 or 4,000 years, however long people have been doing mathematics, still remain unsolved. And so, in particular, is the twin prime conjecture, which has been around. Very debatable. Could have been around for about 2,000 years. People have come up with this conjecture, and it goes like this. So twin primes are primes. It's a pair of primes whose difference is 2. So, for example, 3 and 5 is an example of a twin. Are examples of twin primes. Because their difference is 2. 5 and 7 also are twin primes. Maybe I should do something else. 3 and 5. 5 and 7 are twin primes. 7 and 11 aren't because their difference is 4. 11 and 13, though, those are twin primes. 17 and 19 are twin primes. Any two primes with a difference of 2, so a number gap of 2 is a twin prime. 29 and 31 is twin prime. 41 and 43. There's lots of twin primes. And so the question is, how many twin primes are there? And another thing's true, right? That even as we go forward, right, these twin primes will get sparser, but we'll always be able to find, or at least that's the claim, we always seem to be able to find a twin prime pair. So like these first two, this is starting at the 1,000th prime, by the way. So we don't see any twin primes in these first ones, but then here we get a twin prime. 7,949 is prime, and also 7,951 is prime, and their difference is 2. So these are twin primes. So it seems, with all the primes that we know, and we know a lot of primes, that anywhere we look, we can find a twin prime. There's always a twin prime somewhere. We've never exhausted the twin primes. And so the conjecture is that we'll always be able to do this. There are infinitely many twin primes. Now this just seems like, it's something that seems so true because all of the data we have, and we have a lot of data, seems to suggest this is true. But of course, there's no way to check all of the numbers, right? We can't do an exhaustive search for twin primes, and so we need to be really clever about it. Problem is, we're just not clever enough. No one's been able to prove that there are infinitely many twin primes. So there's a Numberphile video that I've linked on the Blackboard that goes along with this that'll tell you a little bit more about the twin prime conjecture and a little bit more about something called just the, what do they call it? The prime gap. So talking about just gaps between primes. And a lot of progress has been made on this, but if you watch the video, you'll see that they admit that even though they have a really good technique and they've proved something It's similar to this, but a little bit weaker. Their method of proof really has no hope of being able to solve the twin prime conjecture, that this still just seems really out of reach. So that's a very interesting one. I encourage you to watch the video and maybe do a little research on your own about the twin prime conjecture. It's very cool. The next unsolved problem is called Goldbach's conjecture. And this is another one of these conjectures that came about because looking at all the data that we have and noting that we have a lot of data, it would seem to suggest something is true. Yet no one's been able to find a proof that it really is true. And it's stated like this. Every even integer, 4 or more, can be expressed as a sum of 2 primes. So for example, 4 is equal to 2 plus 2. 6 is 3 plus 3. 8 we could write as 3 plus 5, sum of 2 primes. 10 we could write as 3 plus 7, or even as like 5 plus 5 is also acceptable. 12 we can write as 5 and 7. 14 we could write as 3 and 11. And we can keep doing this, right? We'll look at every even integer, and rest assured you'll be able to find 2 prime numbers that when added together give you that number. At least that's the claim. At least all the data we have would suggest that, but no one's been able to prove it. So I've also linked a Numberphile video for this one that'll go into a little bit more detail and probably explain it a little better than I have. So if you're interested in this at all, definitely take a look at that. Some really fun stuff.